Hello friends, IBM is here. Today I gathered the courage to come and record multiple choice questions. Those are paper one questions. And I think today we shall start with atomic physics, or I mean atomic structure and particle physics. These are multiple choice questions. I showed you in one of the previous videos how you can answer them without necessarily printing the document. You can have them in soft copy, but I showed you in the previous video how to save them with the solutions in soft copy just for reference. So without wasting time, let me take you to atomic structure and particle physics. So here we are, AS Physics 970, it is 9702, multiple choice questions. This is supposed to be unit 9 or the last unit according to me, but it is going to be the first unit to be solved. The order does not matter. Before we solve these questions, I want to let you know that actually for paper 1, multiple choice questions, atomic structure and particle physics is going to be the last 3 multiple choice questions, most likely, if not 2. Most likely it is the last 3 multiple choice questions. And I bet that the questions will not be new at all. They will be the same multiple choice questions, maybe sometimes slightly modified, but they will be part of these ones. So when you go through these multiple choice questions, you gain confidence with them, you'll be able to answer those last 3 multiple choice questions in paper 1. Let's start. An alpha particle passes close to a gold nucleus and is deflected through an angle greater than 90 degrees. When we see angle greater than 90 degrees, the first thing to come into our minds is actually the second observation from Rutherford's alpha scattering experiment. Which property of the alpha particle changes as a result of the deflection? So which property changes? Of course, charge cannot be changed by deflection. Momentum could change because momentum is a scalar quantity. When there is a change in direction, the momentum could change. Nucleon number, it does not change if it is the same alpha particle. Proton number will not change if it is the same alpha particle. So we are seeing that the only property which is most likely going to change is actually momentum, because momentum is a vector quantity. If there is a deflection, direction changes. So the answer is going to be momentum. A nucleus of uranium-238-92 decays in stages by emitting alpha particles, beta minus particles. This is beta minus. Remember, I have been saying in AS, if they don't tell us that is beta plus, it is always beta minus. When they just say beta particles, it is always beta minus. So eventually forming a nucleus of lead-206-82. How many alpha particles and how many beta minus particles are emitted during this decay, during the decay chain? So we just write an equation, uranium-238-92 should give us a given number of alpha particles. I'll call that one X alpha particles. But remember, an alpha particle is a helium nucleus, so that is alpha 42. Plus, let's say it gives us Y beta particles. Let's say Y beta particles. Beta is beta. I can just write beta minus. Remember, is 0, -1. Okay, so what determines these particles? Note that, I want you to note that the nucleon number, beta particles, when you look at the symbol, the nucleon number of lead is not determined by how many beta particles are emitted. So the nucleon number of lead is 206-82. The nucleon number of lead is only determined by the number of alpha particles. Therefore, I will say 238 on the left hand side should be equal to X times 4, that is 4X. That is the nucleon number. Y times 0, that is not going to be very important, plus 206. So I try to find X. So I'll say 238 minus 206 divided by 4 to find X. It means X is equal to 8. So there are 8 alpha particles, to be precise. There are 8 alpha particles. So it means we have eliminated C and D. We have A and B. Since we have 8 alpha particles, we can now tell the number of protons. Since x is now 8, we can now find y. So let's consider proton number, conservation of proton number. On the left-hand side, we have 92. It should be equal to the right-hand side, x is 8 times 2. We are looking at proton numbers. So 8 times 2, which is 16, plus y times -1, that is negative y, then plus 82. So we want to find y. So y is going to be, making y the subject, we have 92 minus 16 minus 82, which gives us -6. -6 is equal to negative y. So it means y is 6. Y is 6. So there are 6 beta particles. Therefore, the answer is going to be A. Which list of particles contains only fundamental particles? Only fundamental particles. Remember, fundamental particles are particles which cannot be broken down any simpler. These should not be having any smaller particles within them. We can use elimination method. We know that a meson is made up of a quark and an antiquark. A quark and an antiquark, so that means this column, that one is not going to be fundamental particles because a meson is broken down and is broken down further. It is an antiquark and a quark. Baryons are either protons and neutrons. They are made up of quarks, so this one is not fundamental. Electron, neutrino, alpha particles. Alpha particles have protons and they have neutrons, so they are made up of quarks. That one is not fundamental. Lepton, quark, and positron. So these are the simplest. The quark is not broken down. The leptons, such as the electron, the neutrino, and the antineutrinos are not broken down any further. Those are leptons. The positron is actually the anti-electron. It is not broken any further, so the answer is going to be D. In the alpha particle scattering experiment, a beam of alpha particles is aimed at a thin gold foil. Most of the alpha particles go straight through or are deflected by a small angle. A very small proportion are deflected by more than 90 degrees, effectively rebounding towards the source of the alpha particle. They are actually rebounding. Which conclusion about the structure of atoms cannot be drawn? The Cambridge examiner makes bold what is most likely going to prevent the student from scoring the mark is actually made bold. That is how generous the Cambridge examiner would be. Which conclusion about the structure of atoms cannot be drawn from this experiment alone? First of all, from the alpha scattering experiment, we saw that most of the atom is empty space. So most of the atom is empty space. Most of the mass of an atom is concentrated in the positively charged nucleus. That one can be drawn from the alpha particle scattering experiment. The nucleus contains both protons and neutrons. This one is hard. We can confirm protons because the nucleus is charged, but we cannot confirm neutrons by just looking at the alpha particle scattering experiment. But the nucleus is charged. This one can also be confirmed. Therefore, the answer is going to be C. Okay. So the nucleus contains both protons and neutrons. This one is hard to confirm from the alpha particle scattering experiment because the neutrons having no charge, they cannot be deflected by the nucleus, positively charged nucleus, so we cannot confirm that. So the answer there is going to be C. Okay. Which two particles have opposite charges? Okay, let's see. Alpha particle and helium nucleus. These ones have the same charge. An alpha particle is a helium nucleus. Antiproton and beta plus. An antiproton has charge of positive E. Beta plus has charge of positive E. So these ones, they have the same charge. Beta minus particle and an electron. Beta minus is negative E, an electron is negative E. Okay. Then a positron and a proton. Or let me go back slightly. I think I made a mistake. Alpha particle is a helium nucleus. The charge is positive 2e. This is positive 2e. A helium nucleus is positive 2e. Antiproton. The antiproton has a charge of negative e. It is a proton has positive e, antiproton is negative e. Then beta plus has positive e. So these ones have opposite charges. Therefore, we are saying, okay, beta minus has negative e. The electron has negative e. Then the positron has positive e. The proton has positive e. So which two particles have opposite charges? So here the answer is going to be B. The antiproton has a negative charge, that of the electron. In fact, the antiproton is the negative is the antiparticle of the electron. Which particle is a lepton? So a lepton is not affected by any strong nuclear forces. A lepton is not made up of any smaller particles. So a meson is made up of a quark and an antiquark. That is not a lepton, it is a baryon. A positron is an anti-electron, that is a lepton. A proton is not a lepton. A quark is not a lepton. So the answer here is going to be B. Which statement about the alpha particle scattering experiment provides evidence for the existence of the nucleus? By the way, when I put ticks, these are just guiding what? The one I circle is the correct answer. So don't be confused with those ticks. Which statement about the alpha particle scattering experiment provides evidence for the existence of the nucleus? A tiny proportion of the alpha particles are deflected through larger angles. That is true. A tiny proportion of the alpha particles are deflected through larger angles simply because there is a charge at the center of the atom. Slow alpha particles are deflected through larger angles. That is not true. That one does not actually provide evidence for the existence of a nucleus. The kinetic energies of the deflected alpha particles are unchanged. That one is not true. The number of alpha particles deflected depends on the thickness. That one does not provide, most of these are true, but they don't provide evidence for the existence of the nucleus. But deflection through large angles of a tiny proportion is what shows that there is a positively charged nucleus. A nucleus X undergoes beta plus decay. The products are a nucleus Y with a proton number Z, a beta particle, and another particle P, as shown here. What is particle P and what is proton number of nucleus X? So a nucleus X is undergoing beta plus decay. So proton number of nucleus Y is Z. So let's say what is particle P and what is the proton number of nucleus X? So because it is a positron is accompanied by a positron is an antiparticle, it is accompanied by a particle which is a neutrino. So we eliminate A and we eliminate A and B because P is mentioned an antineutrino, yet it is supposed to be a neutrino. Then beta plus is written as E01. So it means Z must actually have it must have increased by 1. Z must have increased by 1. So the question is, what is the particle P and what is the proton number of nucleus X? So if I try to write this X, giving us Y proton number Z plus beta plus, which is 01, plus P, which P is the neutrino. So it means here Z should be Z plus 1, so that when we combine this, the proton number is balancing. Therefore, the answer is going to be D. A particle consists of two up quarks and a charm. Two up quarks and a charm. What is the charge of this particle expressed in terms of the elementary charge? An up quark has charge positive 2 over 3e. A charm also has the same charge, positive 2 over 3e. but there are 2 up quarks. So we have 2 times 2 over 3e plus 2 over 3e to get the total charge. So that is going to be 4 over 3e plus 2 over 3e, which is equal to 6e divided by 3, which is equal to positive 2e. So this is going to be D. The answer there is D, positive 2e. A uranium-235 nucleus undergoes a series of nuclear decays to form uranium-234. Which series of decays could give this result? Which series of decays could give this result? So we have uranium-238-92. It is undergoing a series of decays to give uranium-234. So let me write here uranium-234, 92. There's a possibility of it emitting, since we have alpha, beta, and gamma. Gamma does not affect the proton number, so this one I will ignore it. Even if there are 4 gamma rays, that one I will ignore it. Beta, emission of beta minus only does also not affect the nucleon number, so I will also ignore that one. So I have C and D. So let's say it emits alpha particles, that is 4, 2. Let's say plus beta particles, 0, minus 1. Both of them are minus. But how many are these? Let me call this one Y and I call this one X. So it is the alpha particles which determine the nucleon number. So I will consider the alpha particles in determining X. So I'll have that 238 is equal to 234 plus 4x, y times 0, that is 0. So that gives me x. X will be 238 minus 234 divided by 4. It means there is 1 alpha particle emitted. So x is equal to 1 alpha particle is emitted. Now let's balance the proton number. The proton number on the left hand side is 92. On the right hand side, so there is 1 alpha particle. There is 1 alpha particle. Of course, it means D is wrong because D is saying there are 2 alpha particles. Let's check the proton number. So the proton number on the left is 92, on the right should be 92 plus x times 2, which is 2, because x is already 1. Then y times negative 1, so plus negative y. So when you take this, the other side, you get negative 2 equals to negative y. So y is 2. So there are 2 beta particles. Therefore, the answer is C. Which combination of up and down quarks forms a proton? A proton is made up of up, up, down. So this is B. An unstable nucleus. By the way, this is a neutron. This one could be, all of them are hadrons, but we are sure of up, up, down, and up, down, down. Up, down, down is a neutron. This one is a neutron. Up, up, down is a proton. An unstable nucleus decays by emitting beta plus particle. Which statement is correct? Emitting beta plus particle. We have seen that a positron is accompanied by a neutrino. So we are here they are saying an antineutrino is also emitted. So this is automatically wrong. Then a neutron changes into a proton. Let's check. If a neutron N10 changes into a proton P11, balance this equation, I'll put a beta particle which should be 0, negative 1. So this is beta minus, not beta plus. So this one is also wrong. Then mass energy is conserved. Mass energy is always conserved in every nuclear reaction. Let's check the last one. The nucleon number is not conserved. It must also be conserved. So the answer is going to be C. Which statement is correct? This one, when you say nucleon number is not conserved, that reaction cannot occur when the nucleon number is not conserved. There are 3 or 4 things which must always be conserved in every nuclear reaction. Number 1, proton number. Number 2, nucleon number. Number 3 is momentum. And number 4 is mass energy. We must have seen this in paper 2 structured equations. Those 4 must always be conserved in every nuclear reaction. Which statement is not correct? An antineutrino is a fundamental particle, that is true. An electron is made up of a quark and an antiquark, that is not true. A neutrino is a lepton, that is true, that is true. A neutron is composed of 3 quarks, that is true. So the answer here is B, not correct. When alpha particles are fired at a thin metal foil, most of the particles pass straight through, but a few are deflected by a large angle. Which change would not? Which change would not? Which change would increase the proportion of alpha particles deflected by a large angle? So we want more alpha particles to be deflected through a large angle. The first one says using alpha particles with a greater kinetic energy. If they have greater kinetic energy, it means they can easily pass through. So that means it will be a smaller angle. That is not true. Using a double thickness foil. A double thickness foil increases the number of atoms, therefore increases the number of nuclei present. There are more nuclei, so there is a greater chance of an alpha particle coming closer to a nucleus and undergoing deflection. So it means this one will cause a large, this one will increase the proportion of alpha particles deflected. So most likely this is the answer. Using a foil made of a metal with fewer protons, that one reduces the the charge available, so that one reduces the proportion. Using a source emitting more alpha particles per unit time. This one does not increase the deflection as long as they have the same energy and we have the same nuclei with the same atoms in the gold. It means, or in the metal foil, it means they will undergo the same deflection. So that will not affect the proportion of alpha particles deflected in through large angles. If they have the same energy and the metal foil has the same nuclei, then they will undergo the same deflection. So the answer is using a double thickness foil, which means it increases the number of nuclei present in the metal foil. That means there is a greater chance of alpha particles coming closer to a nucleus and undergoing deflection. A nucleus of neptunium-236 contains 93 protons and 143 neutrons. 93 protons, 143 neutrons. This nucleus decays with the emission of an alpha particle. The nucleus formed then emits beta minus particle, which diagram shows the changes in number p of protons and the number n of neutrons in these nuclei. So we are saying first it emits an alpha particle. So let's call it NP. NP, let's call it NP23693. First it emits, it decays with the emission of an alpha particle, giving us a new nucleus X, whose proton number, plus an alpha particle, which is a helium nucleus, 42. Proton number reduces by 4, so this is going to be 2. Nucleon number reduces by 4, that is 232. Proton number reduces by 2, that is 91. So it gives us a nucleus X whose proton number is 91. The number of neutrons is going to be 232 minus 91, which is 232 minus 91, which is 141. So neutron number is 141. So let's first look for that one. The first stage, it changes from neutron number changes from 143 to 141. This one is already wrong because it has gone to less than 141. This one is okay, it has gone to 141. This one is wrong because it has gone above 141. This one has gone to 141. So we have two options, B and D. Let's go to the next part. The nucleus formed then emits beta minus. So we have X, which is 232 91. It is emitting beta minus, so it is giving us a new nucleus Y plus beta minus, which is 0 minus 1. So this should be 92, and this remains 232. So our proton number should go back to 92. That means we have already eliminated B, because B proton number goes to 90. So the answer is going to be D, because D shows when it emits alpha, it first goes to 141 neutron number and 91 proton number, then it goes to 92. So the answer is D. Which combination of quarks could not be the quark composition of the hadron shown? So a hadron has 3 quarks. A hadron must have 3 quarks. Let's check. P is proton, N is neutron, sigma particle of charge negative E, then sigma particle of charge positive E. Then we have U is standing for up, D is standing for down, and S is standing for strange. So let's check the charges. The question is which combination of quarks could not be the quark composition of the hadron shown? So let's check. Of course, we know for the proton, this is fine. For the neutron, that is fine. All that we need to check is for the sigma, because the charges have been given negative E, positive E. So let's check down strange. So down strange, that is negative 1 over 3E plus negative 1 over 3E plus negative 1 over 3E. The charge of down is negative 1 over 3E. The charge of strange is also negative 1 over 3E. So we get the total. The total is actually negative E. So this is negative E. So that means this is correct. So most likely it is going to be B, which is not correct. Let's check. Up, down, strange. An up quark has a charge of 2 over 3E. Then down has negative 1 over 3E, strange negative 1 over 3E. And this gives you a total of 0. So that means sigma plus, the quark composition given, is not correct. So the quark composition given of sigma plus is not correct. So our answer is D, because they said which one is not. When alpha particles are directed at a gold leaf, almost all the alpha particles pass through without deflection. A few alpha particles are deviated through large angles. What are the reasons for these effects? Reason number one, most alpha particles have enough energy to pass right through. We know that for this one, if almost all alpha particles pass through without deflections, because most of the atom is entirely empty space. The second one, a few alpha particles are deviated simply because most of the mass is concentrated in a small positively charged nucleus. So we just look for those two. B, most alpha particles miss all gold atoms. A few alpha particles bounce off gold atoms. The gold nucleus is very small, so most alpha particles miss all nuclei. Occasionally, the path of an alpha particle is close to a nucleus. The positive charge in an atom is not concentrated enough to deflect the alpha particle. Occasionally, an alpha particle experiences many small deflections in the same direction. So the answer is C. The gold nucleus is very small, so most alpha particles miss all nuclei. That is, most of the atom is empty space. Then occasionally the path of an alpha particle is close to a nucleus. That's when it is deflected through large angles. A nucleus X is radioactive and decays into a nucleus Y. X and Y are isotopes. They have the same proton number. Which combination of particles could have been emitted during the decay process? Remember, they should have the same proton number. Okay, so a nucleus X is decaying into a nucleus Y. Of course, this is going to give us their alpha particles and beta minus. So I'll say alpha plus beta minus. Alpha is 4, 2, and beta is 0, negative 1. But remember, they are isotopes. So here is Z and here it is also Z. So let's say X alpha particles are emitted and Y beta particles. So let's use of course Y does not affect proton number. I mean Y does not affect nuclear number. It just affects Y just affects the proton number. So how many protons do we have here? So Z on the left hand side should be equal to Z plus 2x minus Y. In other words, we are saying that Y is going to be equal to 2x. Y is 2x. Let's use nuclear number. Let this be A and let this be A. So on the left hand side, the nuclear number is going to be A. On the right hand side, it is going to be A plus now let this be, because this changes, A minus 4. Okay, so this one reduces by 4. So that is A minus 4. Okay, let me use a different letter. So this will be A minus, actually it will be A minus 4 times x. A minus 4 times x. A minus 4 times x. Because the other one is going to actually be 0. How should I do this mathematically? Because I want you to see. Let me use a different letter here. Let me use I want to use a different letter here. Okay, so because the proton number is supposed to be Z, let me use a simpler method. Because the proton number is supposed to be Z, yet here this is 2 times x, and the proton that means the total proton number will be Z plus 2x. Yet it should go back to actually it should go back to Z. So it means most likely x is going to be 1. If x is 1, let's say if x equals to 1, then y is going to be 2. That means if one alpha particle is emitted, then there are 2 beta particles emitted, because y times negative 2, that y times 2 times negative 1 to give us negative 2, which if x times 2 is also 2, it means negative 2 and 2 cancels out. Let's check. One alpha particle. So here there are 2 alpha particles. So one alpha particle, and how many beta particles? If we say 1 beta particle, it means there is no balance. It means y is 1. So it means here we have 2, and the other one we have negative 1. It means there is no balance. If one alpha particle and 2 beta particles, one alpha particle, x is 1, and 2 beta particles, y is 2, so there's a balance. This is 2 plus negative 2, which is 0, so z is balancing, so the answer is going to be B. Okay. A positively charged meson. A meson, remember, it is a quark and an antiquark. What could be the quark and antiquark? It is a positively charged meson. So it has a quark and an antiquark. So let's check. Charm and anti-charm. Ant-up. Charm and ant-up, that is positive 2 over 3e plus ant-up is negative 2 over 3e, that is 0. So this one is not a positive one. Down is negative 1 over 3e, and ant-top, because top is positive, ant-top is negative, so that is negative 2 over 3e. And this one is automatically going to give us a negative e as the charge. So this one is also not positive. Strange and ant-bottom. Strange is negative 1 over 3e. Ant-bottom. Bottom itself is negative, ant-bottom is positive. So that is 1 over 3e. The charge of ant-bottom is positive because the charge of bottom is negative. For those who may not have seen this, let me write the charges here for each of these quarks. Up, up, charm, top. Then up is down, charm is strange, opposite, top is bottom. All these ones have charge of positive 2 over 3e. And all these ones have charge of negative 1 over 3e. Then their antiquarks reverse. Ant-up will be negative 2 over 3e, ant-charm negative 2 over 3e, ant-top negative 2 over 3e. Then ant-down now will have positive 1 over 3e, ant-strange positive 1 over 3e, and ant-bottom positive 1 over 3e. So strange, we have seen that this one is going to give us negative 1 over 3e, and ant-bottom, this gives us 0. Let's check up. Up is 2 over 3e, anti-strange is positive 1 over 3e, which gives us, this is positive 3e over 3, which is e, so the answer is D. That's the one which gives us a positively charged meson. Carbon-14 decays into nitrogen-14 by emitting a beta minus particle. Which statement explains why the beta minus particles are emitted with a range of different kinetic energies? We have seen that when beta minus particles are emitted, they are accompanied by beta minus is a normal electron, it is accompanied by an anti-neutrino. So the energy is going to be shared with the antineutrinos, giving the beta minus particles a range of energy. So number one, the carbon-14 nuclei have slightly different masses. That one does not answer that question. The emitted beta minus particles have range of different masses. That one does not answer that question. The energy released in the decay process is different for each carbon-14 nucleus that decays. That one does not also answer that question. The energy released in the decay process is shared between the nitrogen nucleus, the beta minus particle, and the neutrino. That answers that question. So the answer is D. Because the neutrino accompanies, the energy emitted is shared, making the beta minus particles to have ranges of energies. A nucleus of a radioactive element emits an alpha particle, then a beta minus, and then another beta minus. Which statement describes the final element that is produced? Let's check. A nucleus emits an alpha particle. So it gives Y plus alpha, which is 4,2 plus beta minus. In other words, it's giving 2 beta minus 0, negative 1. So it means it must be having the same proton number. The emitted nucleus has the same proton number as X. Because if the proton number reduced by 2 and again it increased by 2, it means it is an isotope. So it is a different element of higher proton number than the original element. That is not true. It is a different element of a lower nucleon number than the original element. That's also not true, because it is a different element of a lower nucleon number than the original element, the final element. It is not a different element, it is actually the same element, but of course it has a lower nucleon number because the nucleon number reduces by 4. Then it is an isotope of the original element. That is very true. They have the same proton number. So it is an isotope of the original element. It is the same element as the original element, but with different proton number. If it has different proton number, then it cannot be the same element. So it is not. It is only the same element if the proton number has not changed, even if the nucleon number has changed. How many hadrons, baryons, and mesons are there in a nucleus of Be 9494? So there are 4 protons and 9 minus 4, 9 minus 4, those are 5 neutrons. So plus 5 neutrons. So 4 protons, those are 4 baryons. 5 neutrons, those are 4 baryons, and they are also hadrons. So hadrons are 9 because there are 4 protons, there are 9 hadrons, so A and B are still intact. A, B, and C are still intact. We have eliminated C. Then we go to baryons. A proton is a baryon, a neutron is a baryon. So there are 9 baryons because a proton is a baryon and a neutron is a baryon. So there are 9 baryons. So we have eliminated this one, we have eliminated this one, we remain with the C. So we can't eliminate any further because we had already eliminated D, so we remain with the answer as C. Because a proton and a neutron are baryons, there are 4 protons and 5 neutrons. Those are 9 hadrons, 9 baryons. So the answer is C. In an experiment on alpha particle scattering, alpha particles are directed at a thin gold foil. Most of the alpha particles pass straight through the foil or are deflected by a small angle. A small number are deflected by a large angle. Which statement cannot be deducted from this experiment? So this is a similar question but slightly modified. We have answered such a question previously. So atoms are mostly empty space. That is true. That one can be deduced. Most of the mass is concentrated in the nucleus. That one can also be deduced. The nucleus of an atom contains protons. The nucleus of an atom contains protons. The nucleus of an atom is small compared to the size of the atom. This one is also true. This one cannot easily be deduced from that experiment. Although we can conclude that actually the atom is positive, the nucleus is positively charged. So, but we cannot directly come up with a conclusion that the nucleus of an atom contains protons by simply looking at the alpha particle scattering, because the nucleus also contains neutrons. The nucleus also contains neutrons. So the alpha particle scattering experiment does not, we cannot deduce that the nucleus of an atom contains protons by simply looking at the alpha particle scattering experiment. But the rest, there is a large deflection. Atoms are mostly empty space. Most of the mass of an atom is concentrated in the nucleus. The nucleus of an atom is small compared to the size of the atom. All these ones are related, apart from C. 4 nuclei represented below. So this one is, which statement about these nuclei is correct? An uncharged atom of Q has 24 orbital electrons. That is, let's see, Q has 13 protons, so the number of orbital electrons can't be 24, they must be 13. Number of protons should be equal to the number of electrons for the atom to have charge 0. Nuclei G and M are isotopes. We look at proton number. G and M, so they are not isotopes. The proton number is different. When E absorbs a neutron and then emits an alpha particle, E transforms into M. Let's verify. E is E2814. They said it absorbs a neutron, so I'll add a neutron this side plus a neutron. So this gives us another nucleus. Let me call it Y. They said when E absorbs a neutron and then emits an alpha particle, E transforms into M. So it emits an alpha particle. Alpha is 42. So this is going to be 1 plus 28. This side will have 29. The other side will have 29 minus 4, which is 25. Then nucleon number 0 plus 14. This side will be 14 minus 2, which is 13. 12. 12, 25, that is M. And I think this is true. When M emits a beta minus particle, M transforms into Q. Let's see if this is correct. M is emitting beta minus, which is E0 negative 1. So plus M is 25, 12. So this is going to be another nucleus Y, which is 25, and this must be 13. They said transforms into Q. So proton number is 13, but nucleon number is not 25. So that is not true. So the answer is C. A neutron is composed of one up quark and two down quarks. When a neutron decays to a proton, a beta particle is emitted. What is the change in the quark structure of the neutron due to the emission of the beta particle? So they are saying a neutron decays into a proton. So a neutron has up, down, down, and is changing to up, up, down. That means a down quark must have changed to an up quark. So we first eliminate C and D. We have A and B. So whenever a beta minus particle is emitted, it is a normal particle. It is always accompanied by an antiparticle, which is an antineutrino. This makes the answer to be D. It can't be E because a neutrino is emitted when beta plus is the one which is emitted. That is when a proton changes into a neutron. An actinium nucleus has nucleon number 227 and the proton number 89. It decays to form a radium nucleus, emitting a beta minus particle and an alpha particle in the process. What are the nucleon number and proton number of this radium nucleus? So it has nucleon number 227 and proton number 89. It decays to form a radium nucleus. So actinium, I don't know how they write it. Maybe it is like that, but that is for chemistry. Then radium, I think radium is Ra. That is for chemistry. For us, we just want to balance. So nucleon number here is 227. Proton number here is 89. It gives us radium emitting a beta particle, so plus beta minus, which is 0, negative 1, and an alpha particle, which is 4, 2. So nucleon number is going to be 227 minus this 4. That is going to be 223. So nucleon number is 223. So we eliminate C and D because those ones have different nucleon numbers. Then proton numbers, we have 89 on the left hand side, and we have, let me call this one X. So 89 should be equal to X minus 1 plus 2 because this is a negative 1. So it means X is going to be 80. X is going to be 80. That is 80 what? So that is going to be, okay. X is going to be 89 plus 1 minus 2, which is it 90, 80 what? 88? Yes, x is 88. So the answer is going to be B, 88. Which statement is not correct? A meson consists of 3 quarks. That is not correct. A meson consists of a quark and an antiquark. So that is the answer. A proton is a baryon. That is true because it has 3 quarks. A quark is fundamental. That is true. It is not broken down any further. There are 6 flavors of quarks. That is true, which is up, down, top. We have strange, we have charm, and bottom. Those are the 6 flavors of quarks. So a meson consisting of 3 quarks, that is not true because a meson is a quark and an antiquark. Which law describes the relative ionizing power and the relative penetrating power? And the relative penetrating power per unit length in air of alpha and gamma radiations. Of course, gamma is more ionizing, more penetrating than alpha. So we can start by that. We know that gamma is most penetrating. So if there is anywhere they said it is least penetrating, then we can cancel out that. So here they said gamma is the least penetrating. That is not true. And they are saying gamma is the most ionizing. That is not true because gamma have no charge, and ionization mostly depends on charge. And gamma is the least penetrating, least ionizing, but alpha is not the most penetrating. That means D is also wrong. D is saying alpha is the most penetrating, yet it is gamma which is the most penetrating. So although alpha is the most ionizing, gamma is the most penetrating. So the answer is C. A nucleus of sodium decays to form a new nucleus containing 10 protons and 11 neutrons. Which leptons are emitted from the sodium nucleus during the decay? So sodium 2111 is giving us a new nucleus which contains 10 protons and 11 neutrons. So 10 plus 11, that is 21. It has 10 protons and 11 neutrons. So 10 plus 11, that is 21. Okay. So which leptons are emitted? So you see the nucleon number has not changed, the proton number has reduced. So this should be actually a proton. Beta plus. So this should be beta plus 0 positive 1 so that the proton number is also increased. And whenever beta plus is emitted, it is a positron, it is accompanied by a neutrino. So this is accompanied by a neutrino or the electron neutrino. So this is a neutrino. Therefore, the leptons emitted are the positron and the neutrino. And there the answer here is going to be B, a positron and a neutrino. A neutron decays to form a proton. Which particle is not involved in the decay process? A neutron is forming a proton. Neutron is 1, 0, proton is 1, 1. To balance the equation, this will be beta minus 0, negative 1, so that the proton number is also 0. Of course, beta minus, this is a normal electron. It is accompanied by an antineutrino, which is written like that. That is the antineutrino. So which particle is not involved in the decay process? So a positron is there. An antineutrino is there, so this is there. The positron is there. And no, not a positron. This is an electron. A down quark, because a neutron is up, down, down, and changes to up, up, down. So a down quark is involved, an up quark is involved because a down quark changes to an up quark. So it is the positron which is not involved because the beta minus is an electron. Okay. An unstable nucleus of an element decays by emitting an alpha particle or a beta minus particle to become a nucleus of a different element. This nucleus is also unstable and also emits an alpha particle or a beta particle. The process continues. The process continues until an isotope of the original element is produced. What is the minimum possible number of these particles emitted? So let's check. Let's say the nucleus is going to be, let's say the nucleus is X, nucleon number is A, proton number is Z. It is going to emit or to give us a nucleus Y plus several alpha particles, let's say X alpha particles, and alpha is 4, 2, and Y beta minus particles, beta minus is 0, negative 1. Note that it is the nucleon number, it is the alpha particles which is going to determine the nucleon number, because the beta particles will not determine the change in the nucleon number. So since it is the alpha particles which are going to determine the nucleon number, it means it is going to actually emit alpha particles, and the number of alpha particles, because it goes back to the original element, so that they have it is an isotope, so this is going to be Z. So to make sure that